Welcome to Understand the Math. Before you begin, be sure to check out the video description below for a link to free guided notes that you can download and fill in as you watch this video. This is the last part of a 7-part series on topics that commonly appear on an introductory linear algebra midterm or final exam. This video goes over 9 topics related to orthogonality. We'll begin by defining the norm of a vector, a unit vector, and a standard unit vector, and we'll do an example of each one. The norm of a vector is the measure of its length or magnitude. Let's start with a vector v in R2 equal to v1, v2, and look at its graph. This is our vector v. Its x component is v1, and its y component is v2. Let's note that this is a right triangle. The Pythagorean theorem tells us that the length of vector v is the square root of v1 squared plus v2 squared. Likewise, a vector in R3 has a length equal to the square root of v1 squared plus v2 squared plus v3 squared. We can then extend this concept to Rn, even though we can't visualize it, and we can say that the length or magnitude of a vector in Rn is the square root of v1 squared plus v2 squared all the way up through vn squared. Let's now do an example. We're given v is equal to minus 311, and we're asked to find the norm of v. This is a vector in R3, so let's write down the formula. The norm of v is equal to the square root of v1 squared plus v2 squared plus v3 squared. And this is equal to the square root of minus 3 squared is 9 plus 1 plus 1. And we get an answer of the square root 11. So the length of vector v is equal to the square root of 11. A unit vector is a vector of norm or length equal to 1. A unit vector u that has the same direction as a vector v can be written like this. U is equal to v divided by its magnitude. The process of multiplying a vector by the reciprocal of its length is called normalizing a vector. So in our red box there, we normalized vector v. In this example, we're going to find a unit vector u that has the same direction as v. Let's write down our formula. Our u is equal to v divided by the magnitude of v. The magnitude of v is going to be equal to the square root of minus 3 squared, which is 9, plus 1 squared, plus another 1 squared is root 11. And that tells us that u is equal to minus 3 over root 11, 1 over root 11, and then 1 over root 11. Let's now define what a standard unit vector is. Standard unit vectors are unit vectors in the positive direction of the coordinate axis. In R2, our standard unit vectors are E1 and E2. If you've studied physics, you might recognize these as I hat and J hat. In R3, our standard unit vectors are E1, E2, and E3, or in physics, you would call these I hat, J hat, and K hat. This concept then extends to Rn, and our standard unit vectors are E1, E2, all the way up through En. Any vector can be written as a linear combination of the standard unit vectors. In this example, we're going to write our given vector v as a linear combination of the standard unit vectors. Our v then is going to be written as v1 e1 plus v2 e2 all the way up through vn en. We're now going to go over how to calculate the distance between two vectors. We'll start with finding the distance between two vectors in R2. We have a vector u given by x1, y1, and we have a vector v given by x2, y2, and we want to calculate the distance between these two vectors. Let's remind ourselves that these two distances are equal to x2 minus x1 for the bottom leg, and then this other leg is going to be y2 minus y1. So the distance between these 2 points, P1, P2, is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. You may be already very familiar with that formula. What we're going to do now is we're going to write this distance in terms of our vectors u and v. So we say that the distance is equal to the norm of u minus v, or we could write that as the norm of v minus u. We can then extend this concept to Rn and write down the distance between u and v. That distance is going to be the square root of u1 minus v1 quantity squared, u2 minus v2 quantity squared, all the way up through un minus vn quantity squared. This can also be written as magnitude u minus magnitude v. Let's now use this formula in an example problem. In this problem, we're asked to calculate the distance between u and v, and notice that u and v are vectors in R4. Our distance is our magnitude u minus v. This is equal to the square root of 1 minus 0 squared plus 3 minus 7 squared plus minus 2 minus 2 squared, and then lastly 7 minus 2 squared. Let's see what this gives us. This is the square root of 1 plus 16 plus another 16 plus 25, and we add that all up, and we end up with the square root of 58. Let's now talk about the dot product. The dot product is a number. It's not a vector. It's equal to a number. It is a useful multiplication operation on vectors. It is also called a scalar product. And what a dot product does physically is it tells us something about how much two vectors point in the same direction. It is also called the Euclidean inner product. We'll begin our study of the dot product with two vectors, u and v, that are separated by an angle theta. The dot product of u and v is equal to the magnitude of u times the magnitude of v times the cosine of the angle between those two vectors. If theta is an acute angle, it is between 0 and pi over 2, then cosine of our angle is going to be greater than 0, and that's going to tell us that our dot product is going to be greater than 0. If our angle between the two vectors is equal to pi over 2, then our dot product is going to be equal to 0 because the cosine of pi over 2 or 90 degrees is equal to 0. If our angle between the two vectors is obtuse, our angle ranges from pi over 2 to pi, then our cosine is going to be negative, and our dot product is also then going to be negative. For computational purposes, it's very useful to have a formula that expresses the dot product in terms of its components instead of what we just had above in terms of the magnitudes of the vectors and the angles between them. To find the dot product of u and v in terms of u1, v1 and u2, v2, we would use the law of cosines and relate theta to the two sides of the triangle that's shown in this picture. I'm going to skip all those steps and I'm going to show you what we end up with after all the algebra simplifies. We end up with the expression u dot v is equal to u1, v1 plus u2, v2. We extend that concept for a vector that's in Rn, and our formula looks like this. u1, v1 plus u2, v2, all the way up through un, vn. There's a couple of other ways to write this. Since u and v are vectors, we can say that u dot v is the same as u transpose v or v transpose u. Let's now look at two examples where we're going to use this version of the dot product. In the first example, we're going to find u dot v, and we're given u and v. Our dot product is equal to 1 times 0, which is 0, plus 3 times 7, which gives us a 21, and then we have a minus 4, and then our last one gives us a 14. When we add all those up, we get an answer of 31. In our second example, we're asked to compute the dot product of two different expressions that have vectors in them. This is going to equal 3 u dot u plus 4 u dot v minus 6 v dot u, and then lastly minus 8 v dot v. This is going to give us, if we simplify everything, 3 magnitude u squared plus our middle components minus 2 u dot v minus 8 magnitude v squared. And let's just make a note that u dot v is the same as v dot u, and that's why I was able to combine those middle terms. Now that we have some tools in our toolbox, we can start to talk about orthogonality. We say that two vectors are orthogonal if they are perpendicular to each other. In this picture, we have two vectors, u and v, that are perpendicular to each other. So let's make a note that our theta is pi over 2 or 90 degrees. Let's now look at what this dot product looks like. U dot v, using our definition that involves our angle theta, is the magnitude u times the magnitude of v times cosine of the angle between them. So that's cosine 90 degrees. Cosine of 90 degrees is 0. So this is equal to 0. So let's write down if two vectors are orthogonal, their dot product is equal to 0. Let's now do an example. We're given u and v, and we're asked to show that u and v are orthogonal vectors in R4. So all we're going to have to do is take the dot product and see if it's equal to 0. Let's go ahead and let's do that. U dot V is going to be minus 2 times 1 is minus 2. 3 times 2 is a 6. 1 times 0 gives us 0. And then lastly, 4 times negative 1 is minus 4. And we see that that adds up to 0. So they are orthogonal. In addition to checking if two vectors are orthogonal, we can also check if they're orthonormal. Let's define what orthonormal is. An orthonormal set of vectors is a set of orthogonal vectors in which each vector has a norm of 1. So 2 requirements for a set of vectors to be orthonormal. The vectors need to be orthogonal and they need to all have a norm of 1. In this example, we're given 3 vectors, and we're going to determine if the set of vectors is orthogonal for 1, and then if it's orthonormal. And then if it's not orthonormal, we're going to convert it to an orthonormal set. So the first thing we're going to do is check to see if it is orthogonal. We'll mark that with a 1. So let's check that. So V1 dotted with V2. When you multiply out the components, you get a 0, a 0, and a 0, so that's 0. And then V1 dotted with V3 is going to be a 0, and then a 0, and another 0, so that's good. And then lastly, V2 dotted with V3, we get a 1, a 0, and a minus 1, so that's also equal to 0. Great. So our set of vectors is orthogonal. Now let's see if it's orthonormal. We're going to have to look at the magnitude of each vector. The magnitude of V1 is equal to 1. The magnitude of V2 is going to be the square root of 1 plus 1, which is root 2. So V2 does not have a magnitude of 1. Now let's check V3. So magnitude of V3 is going to be, looks like the same thing. 1 plus 1 is equal to root 2. So our set of vectors is orthogonal, but it's not orthonormal. We can, however, make it orthonormal if we divide the vectors by their magnitude. So we can say our orthonormal set is going to be Q1, Q2, Q3, which is going to be V1, V2 divided by its norm. We didn't do that for V1 because its norm was already equal to 1. And then V3 divided by the norm of V3. So this is going to give us, we're running out of space, a 0, 1, 0, a 1 over root 2, a 0, and a 1 over root 2. And then our third vector will be 1 over root 2, 0, and then a minus 1 over root 2. We're going to use this process later on when we do orthogonal diagonalization, so it's good to know how to do it. If you're finding this video helpful, please give it a thumbs up, and if you have time, drop a comment below. This next topic on orthogonal projection is one of my favorites. In many applications, it's necessary to decompose a vector into 2 orthogonal vectors. Our vector u pictured here can be decomposed into 2 orthogonal vectors, which we can call w1 and w2. W1 is the orthogonal projection of u onto vector A, and W2 is the vector component of u orthogonal to A. The projection theorem tells us that if u and A are vectors in Rn and A is not equal to 0, then u can be written in terms of W1 and W2 like this. We say that U is W1 plus W2. W1 lies along vector A, so we say that W1 is a scalar multiple K of A. And then we can also write down that W2 is orthogonal to W1. We're going to use this in just a minute, so let's just do some highlighting. We can say that W1 is equal to K times A, and then from this equation, we're going to say that W2 is equal to U minus W1, and let's highlight that because we're going to need that also in a minute. Our goal now is going to be to write our two orthogonal components of U in terms of U and A. So that means we have to write W1 and W2 in terms of U and A. Here's how we're going to do this. We're going to start by saying U is W1 plus W2. We're going to make use of the fact that W2 and A are orthogonal. Let's look at that again. Our vector W2 is perpendicular to A. So what that means is the dot product of W2 and A is going to be equal to 0. So we're going to take the dot product of each component in that equation with A. So on the left, we have U dot A, and then on the right, we get W1 dot A plus W2 dot A, and we know that this is going to be equal to 0. And then we also know that W1 from up here is equal to K times A, so let's plug that in. So Ka dotted with A plus 0. This is going to give us a value for our scalar K. So this is going to tell us that K is equal to U dot A over A dot A. We can now write what W1 and W2 are in terms of U and A. So W1 is equal to K times A. So W1 is going to be U dot A over A dot A times A. And then W2, pull this down, is going to be U minus W1. So this is going to be U minus what we got for W1. U dot A dot A times A. Okay, we did it. Now we have our orthogonal components of U written in terms of U and A. We say that the orthogonal projection of U on A is written as projection U onto A, and that is equal to U dot A dot A times A. That's W1. And then our next one is W2, the vector component of U orthogonal to A, and that is equal to U minus U dot A dot A times A. Let's now put this theory into practice and let's do an example. We're given two vectors in R3, and we're asked to find the vector component of U along A and the vector component of U orthogonal to A. So we're going to start with a formula. The vector component of U along A is the projection of U onto A. I always have to think about that when I write it, because you say U onto A, but you write A first. So here we go. So this is U dot A over A dot A times A. Sometimes you'll see the A dot A written as the magnitude of A, quantity squared. Let's now compute this. So we're taking U, dotting it with A. So on the top, we're going to get an 8 plus 1 plus 6. And on the bottom, we dot A with itself. So we get a 16 plus 1 plus 4. That gets multiplied by A. When we do that arithmetic, let's see, we get a 15 on top and a 21 on the bottom. So 15 over 21A. We can simplify that by dividing 3 into each. So we have 5/7 A. And then we can write this as, we're going to multiply 5 over 7 times our components of A. So we get a 20 over 7, a minus 5 over 7, and then lastly a 10 over 7. Okay, great. That one's done. Let's do the next one. The next one's a little bit easier. The vector component of U orthogonal to A, that is the vector U minus the projection of U onto A, which is what we just found. So this is going to be our U, 2 minus 1, 3, minus what we just found, 20 over 7, minus 5 over 7, 10 over 7. So this gives us a minus 6 over 7, a minus 1 plus 5 over 7, which gives us a minus 2 over 7. And then lastly, 21 minus 10 gives us an 11 over 7. Let's now revisit the topic of linear combinations. I went over this topic in the Linear Algebra Review series on vector spaces. In this video, we're going to talk about linear combinations for vectors that are orthogonal. We'll begin by reviewing how to write a vector as a linear combination of a set of vectors in a basis. We start with a vector U, that is a vector in a basis that contains vectors E1 up through En. And we want to write U in terms of a new set of basis vectors. And that new set of basis vectors contains the vectors V1 through Vn. So we say that U can be expressed in terms of basis B by writing U as a linear combination of the basis vectors in B. To find our values for K, what we did was we took our vectors V1, V2, all the way up through Vn and put it in an augmented matrix with U, put that matrix in reduced echelon form, and found our Ks. That's how you express a vector as a linear combination of other vectors when those vectors are not orthogonal. This then gave us our coordinate vector in terms of our basis beta as K1, K2, all the way up through Kn. That was a pretty lengthy process. Now what we're going to learn that there's an easier way to do this if our vectors V1 through Vn are orthogonal. So let's go over the procedure to find our Ks when our vectors V1 through Vn are orthogonal. We begin just like we did before. We write U as a linear combination of our vectors V. To find K1, we're going to use the fact that all the V vectors are orthogonal. So we're going to take the dot product of this equation right here with V1 in order to find K1. So we're going to have U dot V1 is equal to K1 V1 dot V1 plus K2 V2 dot V1 all the way up through Kn Vn dotted with V1. We then see that V2 dotted with V1 is 0 because the vectors are orthogonal. Same thing with all the other vectors. These are orthogonal. So that just leaves us this part of the equation, and we can then solve for K1, and we write K1 as U dot V1 divided by V1 dotted with V1. To find K2 all the way up through Kn, we would do that same type of procedure. To find K2, we would dot that equation with V2. Let's now summarize what we found. Our basis vectors are equal to V1 all the way up through Vn, and we've denoted our basis by S. U sub S is our coordinate vector of U relative to S, and that coordinate vector is equal to U1 dotted with V1 divided by V1 dot V1. That was our K1 from above. And then our K2 is U dotted with V2 over V2 dotted with V2 all the way up through our component U dotted with Vn divided by Vn dotted with Vn. Let's now walk through an example. We're given three vectors, v1, v2, and v3, and we're asked to express u as a linear combination of these three vectors when u is equal to 1, 1, 1. The first thing that we're going to do is we're going to check to see if the vectors are orthogonal, because if they are, we can use this easier method. So we compute v1 dotted with v2, and we see that we get 0. We compute v1 dotted with v3, and we again get 0. And then lastly, we compute v2 dotted with v3, and for that one, we end up with a minus 12 over 25 plus 12 over 25, and that one is also equal to 0. So that means our vectors are orthogonal, and we can use this easier way to write u as a linear combination of those vectors. Our u is equal to k1 v1 plus k2 v2 plus k3 v3. Our k1 is going to be u dotted with v1 divided by v1 dot v1. And that's going to be a 1 on top. And in the denominator, v1 dotted with itself is also going to be 1. So k1 is 1. K2 is equal to u dotted with v2 divided by v2 dotted with v2. Let's see, u dotted with v2, we get a minus 4/5 plus a 3/5 is minus 1/5. And then the denominator, v2 dotted with v2, we get a 16 plus a 9, which is 25 over 25 is 1. So this is minus 1/5. And then we continue that same process, and we find that k3 is equal to 7 over 5. Our vector u then can be written as 1 times v1, so v1 minus 1/5 v2 plus 7/5 v3. Our next topic is the Gram Schmidt process. The Gram Schmidt process is a process to transform a set of basis vectors into an orthogonal or orthonormal set of basis vectors. We start with a set of basis vectors, then we do the Gram Schmidt process. To end up with a set of orthogonal basis vectors. And then we often want to make those vectors orthonormal, so we normalize them. And we go through a normalization process to get the orthonormal basis vectors. Let's now see how the Gram Schmidt process works. We start with a basis that does not contain orthogonal vectors. We'll let that basis contain the vectors u1, u2, and u3. We then want to create an orthogonal basis, which will indicate by vectors v1, v2, and v3. We choose our first orthogonal vector v1 to be equal to u1. And then what we're going to do is we're going to make v2 orthogonal to v1. And the way that we do that is we set it equal to u2 minus u2 dotted with v1 divided by v1 dot v1 times v1. Let's make a note that this expression right here is the projection of u2 onto v1. There's a lot of great videos out there that animate the Gram Schmidt process that I would suggest that you also watch. v2 is the vector perpendicular to v1. v3 is equal to u3 minus u3 dotted with v1 divided by v1 dot v1 times v1 plus u3 dotted with v2 divided by v2 dot v2 times v2. This component here is the projection of u3 onto the plane spanned by v1 and v2. Let's now walk through an example. We're given three vectors, u1, u2, and u3, and those vectors are in a basis, and we are asked to transform that basis into an orthogonal basis and then into an orthonormal basis. We'll begin by letting v1 equal to u1, and this is equal to 1, 1, 1. v2 is equal to u2 minus the quantity u2 dot v1, v1 dot v1, v1. This becomes 0, 1, 1 minus u2 dotted with v1. Let's make a note. This vector is also v1. So u2 dotted with v1 is going to give us a 2 on top, and v1 dotted with itself is going to give us a 3. And that gets multiplied by v1, which is 1, 1, 1. And this gives us, when all the dust settles, minus 2/3, 1/3, and 1/3. And then v3 is going to be u3, notice the pattern, minus u3 dot v1, v1 dot v1, v1, plus, a lot of students make a mistake and put a minus there, plus u3 dotted with v2, v2 dot v2, times v2. So u3 is 0, 0, 1 minus, this expression gives us 1/3. I'm not going to walk through it. You can do that on your own and stop the video. So 1/3 times 1, 1, 1. The biggest mistake I see is that this does not carry through over to here. So that becomes a minus, and that is a minus 1/3 on top. And down below, we have a 4/9 plus 1/9 plus 1/9. And that is multiplying our V2, which we just found to be 2/3, 1/3, 1/3. Lengthy calculation. When all the smoke clears, we end up with a 0, a minus a half, and a minus a half. We now found V1, V2, and V3. So we have an orthogonal basis. Let's highlight those answers in green. So we have V1, V2, and V3. Now the last step of this process is we want to create an orthonormal basis. We have to find the magnitude of our new orthogonal vectors. So the magnitude of V1 is √3. The magnitude of V2, and that gives us a √6/3. And then lastly, the magnitude of V3 is 1 divided by √2. Our orthonormal vector Q1 is going to be V1 divided by √3. So this is 1/√3, 1/√3, 1/√3. Our Q2, and when all the smoke clears, this becomes minus 2/√6, 1/√6, 1/√6. And then lastly, Q3 is going to be equal to our V3 times √2. So that gives us a 0, a minus 1/√2, and a 1/√2. Probably be a really good idea to stop the recording and make sure you know how to do this problem and maybe redo it by yourself. The 9th topic that we're going to go over is orthogonal diagonalization. Before we go over that topic, we need to learn a little bit about orthogonal matrices. We're going to assume that we're given A and it's an orthogonal matrix. There's 3 properties that I want to highlight for our orthogonal matrix A. The first property is that it's a square matrix. The second property is that A inverse is equal to A transpose. I'm going to put a star by that one because that's the one that we're going to use. And another way of saying A inverse is equal to A transpose is if we multiply the right or the left by A, we would get A transpose is equal to A transpose A is equal to the identity, because A times A inverse is equal to the identity. We're going to use the property that I starred to determine if a matrix is an orthogonal matrix. In this example, we're given a matrix A and we were asked to find if it's an orthogonal matrix. Let's compute A inverse. So A inverse is 1 divided by the determinant of A. So this is cosine squared theta plus sine squared theta. And we multiply that by cosine theta. Those two change, but they're the same, so they remain the same. And then the sign changes on these other ones. So this becomes sine theta minus sine theta. So this is equal to cosine theta minus sine theta, and then sine theta, cosine theta. Because cosine squared theta plus sine squared theta is equal to 1. Now let's compute A transpose. We take A, we switch the rows and the columns. So the first row of A becomes the first column of A, and then the second row of A becomes the second column of A. And we can see that these two matrices are the same. So that tells us that A is indeed an orthogonal matrix. This brings us to our last topic. Our last topic is learning how to orthogonally diagonalize a matrix. Before we begin, let's review diagonalization. I went over this topic in the Linear Algebra Review series on eigenvalues and eigenvectors. You may want to check that out if you haven't gone over diagonalization before. To diagonalize a matrix, we're going to write it as A is equal to P times D times P inverse. P is a similarity matrix that diagonalizes A, and D is equal to P inverse AP, and it's a diagonal matrix that is similar to A. When we orthogonally diagonalize a matrix, our job is to find P and D. Since P is an orthogonal matrix, we're going to replace P inverse with P transpose. So D is equal to P transpose AP. So we say that D, written in this form, is a diagonal matrix orthogonally similar to A. We can also get a new formula for A. So our A was equal to P D P inverse. Now replacing P inverse with P transpose, we get that A is equal to P D P transpose. We say that P orthogonally diagonalizes A, and also A is orthogonally diagonalizable. Let's now go over the requirements for a matrix to be orthogonally diagonalizable, because we don't want to start this process until we know if the matrix can be orthogonally diagonalized. Our theorem states that the following are equivalent for an n by n matrix with real entries. So we can say if A is orthogonally diagonalizable, then A has an orthogonal set of n eigenvectors, and then likewise A is symmetric. And let's just remind ourselves, if A is symmetric, A is equal to A transpose. So the way this works in practice is we'll know if a matrix is orthogonally diagonalizable if it's symmetric. Because if it's symmetric, it's guaranteed to be orthogonally diagonalizable. And then we can also say if it's orthogonally diagonalizable, we're going to get an orthogonal set of eigenvectors. Symmetric matrices arise a lot in applications. Let's go over two properties of symmetric matrices. If A is a symmetric matrix with real entries, then we say that the eigenvalues of A are real numbers, and that the eigenvectors from different eigenspaces are orthogonal. Let's now go over a procedure to orthogonally diagonalize a symmetric matrix. As a review, let's go over the two steps that we did to diagonalize a matrix. The first step was we found the eigenvalues and constructed D, and then we found the eigenvectors and constructed P. To orthogonally diagonalize a symmetric matrix, there are three steps that we're going to have to follow. The first step is the same as the first step above. We're going to find the eigenvalues. And construct D. The second step is we're going to find a basis for each eigenspace of A. And then we're going to use, I'm going to abbreviate it by GS, we're going to use the Gram Schmidt process to obtain an orthonormal basis for each eigenspace. And then we're going to construct P. In my experience, working with students on these three steps is that last step often gets forgotten. So you want to make sure to do that last step. In the example that we're going to look at, we're going to find an orthogonal matrix P that diagonalizes A. The first thing let's do is let's make sure that it's a symmetric matrix. So we can draw a line along the main diagonal and look at corresponding entries. So 2 is equal to 2, this 2 is equal to this 2, and this 2 is equal to that 2. So that tells us that A is equal to A transpose, and our matrix is symmetric. Our first step is to find the eigenvalues and construct D. I'm not going to do that in this video. I went through this on my other video on eigenvalues and eigenvectors. So I'm just going to write down, you would end up with lambda is equal to 8, 2, and 2. Those are our eigenvalues. And our D could look like this, 8, 0, 0, 0, 2, 0, 0, 0, 2. Now we're going to find a basis for each eigenspace. I'm also not going to go through this in great depth because that was gone over in my video on eigenvalues and eigenvectors as well. So for lambda is equal to 2, I'll just go over the procedure. What we do is we take A minus lambda I, augment it with 0, and put it in reduced echelon form. You might want to stop the video and do that on your own, and you're going to end up with U1 is equal to minus 1, 1, 0, and then U2 is equal to minus 1, 0, 1. You may get a slightly different answer than that. Yours may be different than mine by a scalar, and that's okay. It just depends on your choice of the free variable. Then for lambda is equal to 8, we're going to do the same procedure, and we end up with U3, give us a little bit more space here, is equal to 1, 1, 1. Now we want to check to see if these eigenvectors are orthogonal. Let's go ahead and let's do that. So U1 dotted with U2 is going to be 1 plus 0 plus 0, so that's a 1. So already U1 and U2 are not orthogonal. Now let's check U1 and U3. U1 dotted with U3 is minus 1 plus 0, so that's 0. So those two are already orthogonal. And then lastly, let's check U2 and U3. We get a minus 1, a 0, and a 1, so that's 0. Okay, so that's actually pretty good. So 2 of our 3 vectors were already orthogonal. So now our job is just to make U2 orthogonal to U1. And we're going to use the Gram Schmidt process to do that. We will begin by setting V1 equal to U1, and then we'll find V2. So V2 is U2 minus U2 dotted with V1 divided by v1 dot v1 times v1. You might want to stop the video and do this on your own. What we get is minus 1, 0, 1. That's our u2 minus, when we do all the dot products, we end up with a minus 1/2 times our v1, which is minus 1, 1, 0. And that gives us minus 1/2, minus 1/2, and 1. So we now have orthogonal vectors in our basis. The next step we're going to do is we have to make those orthogonal vectors orthonormal. So we'll normalize each vector. So our new set of vectors is going to be v1 divided by the norm of v1, v2 divided by the norm of v2, and lastly v3 divided by the norm of v3. And let's make a note, we didn't compute v3 because v3 we can just set equal to u3 because u1 is orthogonal to u3 and u2 is orthogonal to u3. This new vector is going to go into the first column of P because if we go back up, it is related to lambda is equal to 8, and we put lambda is equal to 8 in our first column. And then our next two vectors can go in the second and third columns. So our P looks like this. 1 divided by root 3, 1 divided by root 3, and 1 divided by root 3. And then we get minus 1 over root 2, 1 over root 2, 0. And then lastly, minus 1 over root 6, minus 1 over root 6, and 2 over root 6. I hope this video series has been helpful to you and it's given you more of an appreciation of linear algebra.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.